So yes, whatever happened to physical dimensions? So I guess the main thesis I'm going to be putting forward today is that there is a disconnect between the familiar use of dimensional analysis and something everyone is familiar with the mathematics that we use for theoretical physics. And I hope to convince you that we are making good progress to actually remedying this disconnect. And I will present my humble contribution to this effort. Well, just to begin, we have to go back to kindergarten. So let's just think about the most basic problem that one can think of in the context of when one is learning science for the first time. So I'm not asking you to read this entire problem, but you can see this could be some textbook science problem. You know, you have two tabs at different flows that you're trying to fill up a cap, and you want to figure out, given the flows, given the volume of the cap, how long it will take. So you can see all the units, all the magnitudes are given with units, and you know all the physical quantities are in different choices of units, and so you have to manipulate. You have to make sure that you add things together in the correct way. But you can imagine someone in high school doing this perfectly fine. I mean, it's very elementary, not just for physicists and philosophers and mathematicians, but anyone who is educated these days will be perfectly familiar with this. So I will try to unravel a little bit the mathematical structure that goes behind this, and sort of my proposal is to formalize what's behind this. But just to give a context and to give sort of an understanding of why I thought of this problem in the first place, I want to give a little bit of history. So I constructed this timeline online. It's not great, but I hope that you can see mostly. Your faces are on the way for me, so let me just move them away for a moment. Um, so what's on this timeline? This timeline is trying to represent, as well as the title says, classical mechanics versus dimensional analysis. I should say a more geometric flavor of classical mechanics. And so I just placed some landmarks on the timeline. I obviously begin at the beginning with the Principia, and then so we have a sort of a symbolic beginning of mechanics at Newton's, for example, and then we have some landmarks, Lagrange's, Hamilton's, Lee's, Wells for gauge theory, and then some reference for what is a modern understanding of classical mechanics, such as Marsden's or Arnold's, could be someone else's. The point here is that I want to emphasize sort of when a subject is sort of beginning, maturing, and being mathematically formalized roughly. I mean, these are very rough dates. And so the key takeaway from this timeline is the fact that dimensional analysis and mechanics are not in phase, right? So this is the main point of why I'm showing this timeline. So perhaps you're familiar with the top timeline, with the classical mechanics timeline. So let me briefly discuss the bottom timeline, which you might be less familiar with. So the bottom timeline is outlining some contributions towards the theory of dimensional analysis, modern dimensional analysis. So of course, both mechanics and dimensional analysis go back to the beginnings of science thousands of years ago. But in its modern incarnation, I think it's fair to say that these are sort of the main moments that, or the main publications that contributed to the current history. So we have a first mention in Euler's theory for rigid solids, but the first systematic presentation of dimensional analysis as we know it today happens in Fourier theory of analytical theory of heat, right? His sort of landmark thermodynamics book. So the subject really starts there as we know it today, and it begins maturing until, so it has contributions from Rayleigh. He has a full chapter dedicated to dimensional analysis, and I think the name is already being used in this way, the theory of dimensions, or the method of dimensions, or something like that, he calls it. And then we have the pi theorem, so the celebrated result where you can identify the minimal dimensionless parameters of a given physical theory characterized by some equations involving dimensioned magnitudes. It was popularized, proved and popularized by Buckingham in I think it was 1914. Around that time, there was also some papers in Nature that launched the theorem into the mainstream. I mean, the theorem had been already pointed out by Rayleigh, although without full proof, and had been fully proven by another French mathematician before. But at any rate, around the time of Buckingham's publications at the beginning of the 20th century, we have the sort of the mature phase of dimensional analysis. So what I want to emphasize here is that by the time that mechanics is reaching its maturity, we have the beginnings of a systematic treatment of physical quantity and dimensional analysis as we know it today. And as a reference for dates, it was around the time when Einstein published his general theory of relativity that we have the launch into the mainstream of dimensional analysis. So that's how different the story of classical mechanics and dimensional analysis is from a historical point of view. And then into the 20th century, we have I always like to think of history as a logarithmic scale, both in terms of resolution of our understanding and probably in regards to science for the pace of development. But as we get into the 20th century, it might look like the formalization of mechanics and the formalization of dimensional analysis are close, but I would say that logarithmically they are equally separate from the previous sort of out of phase or sort of misalignment of the two subjects. So we have around the 70s with where all the differential geometry was sort of coming into its own and all the geometric mechanics. Dimensional analysis was still being discussed and being some work was being done precisely by Hart, but nothing mainstream or nothing well understood was out there for people to use. And then finally, in the last few years, there were a few publications from Vitolo and collaborators who proposed their theory of positive spaces and semi-vector spaces, and in my opinion, that basically mathematically captures in full rigor what dimensional analysis is. So we have a good mathematical theory of dimensional analysis. So I don't want to delve further on this timeline because I would spend too much time sort of explaining the ins and outs of the history, which I think is interesting, but I need to move on. So what's my goal today? So my goal today is to try and discuss the basic features of dimensional analysis and provide a mathematical framework in which we can understand this, and then perhaps, and I hope I'll convince you of this, sort of implement it in classical mechanics, or give a version of classical mechanics that has intrinsically a notion of physical quantity, a notion of physical dimension. So what are the main features of physical quantities? Of course, we have perhaps the most visible and the most jarring for a mathematician is the partial addition. We can't just add two quantities at random. We need to care about type and about units. We have total multiplication, so the same as addition being partial, multiplication is total. We don't need much regard for multiplication when it comes to that. And then units behave multiplicatively. So units are sort of transparent to addition, but they are multiplicative under multiplication, right? So something happens to units when you multiply to physical quantities. And then of course there's the issue of conversion factors. All these things really are sort of equivalence classes of numbers that represent the same physical quantity under the change of units. So these are all the sort of the main formal features that we all know about physical quantities. And my proposal is to capture them in the most simple and minimalistic way possible in a mathematical theory. So my proposal is very naive, and part of the motivation for me to give this kind of presentation is to share my shock of how powerful such a naive choice of generalization really turns out to be for the problem at hand. Meaning, can we put units of measurement into mechanics in a natural intrinsic way? So the choice of what a dimension set is going to be. So I'm basically going to take mathematical sets and I'm going to take sort of a dimension version of them. So I'm going to throw dimensions on top, and that just means I'm going to type them, right? I'm just going to put labels on each of the elements of the set. So I'm going to describe that with a surjection between sets. A set is going to be sort of the main set, and the D set is the dimension set, and alpha is just a surjection. So it's basically the label, right? The reason why I take it to be a surjection is just mostly convenience, that you don't want dimensions that don't refer to anything. In some sense, A is the whole thing, and you just type A. So from a mathematical point of view, I'm going to try and build a category of such things. We begin in traditional mathematics with the category of sets. In this context, I want to build the category of type sets or dimension sets. And all I do is I take morphisms between surjections. This is just these kind of commutative diagrams. Very simple. In fact, this is entirely analogous to categories of bundles in some sort of cosmetic way almost. So because we're interested in an operation that is only defined within a type, I want to start defining binary operations that are only. By the way, I'm gonna call the different subsets of constant type, the so-called fibers of the projection. I call them slices, just not to confuse with fibers of bundles, because there will be bundles at some point in the presentation. So I'm gonna say slice for a pre-image of the projection of the dimension projection alpha, and I'll say fiber for fibers of actual bundles. So what this represents is a slice-wise operation. So this is a binary operation that is slice-wise. I'm interested in recovering something like numbers, so I'm going to start building abelian groups and then try to put some monoid structure on them to make them into rings, because my objective is doing classical mechanics. So I want rings and modules and these kind of things. So an abelian group, or sorry, a dimensional abelian group for me is a dimension set like this with a slice-wise abelian group structure. So these effectively are just families of abelian groups, nothing else. It's a family of abelian groups indexed by the set D of dimensions. So if I then throw, so let me consider a dimension set R a dimensioned set R with a dimension set G with partial addition, making it into an abelian group, or in this context, so dimension abelian group. If I put a total multiplication on top, so that would be the projection, the dimension projection, a total multiplication on the ring, on the set, will be called a ring if the following typical ring axioms hold. So if you notice, if you remove the third one, these are just literally the ring axioms. And so you might look at the first one, actually the first two, and say, well, those are just the axioms for monoid. That's correct. And then the third one is the fact that you should have, by the way, I'm assuming that for reasons that will be apparent in a second, that G must have some kind of monoid structure as well, and the dimension projection must be a morphism of those. But let's not get into the details of that. And then you want to demand distributivity. This is what makes rings rings, right? Now, but you might be wondering, wait a minute, addition is partially defined. How do you do that? That's not trivial anymore. So I use a notation where I denote an element of the ring by A and then a subscript by its projection onto the dimensions. So I rewrite the addition, the distributivity condition like this. So the first A and A prime must have the same sub-index G because they need to be added in one of the plus Ds, right? The abelian groups that are just on one slice. But then I can multiply them by any B sub H, which is an arbitrary element of the ring. And then if I want to demand distributivity, those two elements, A dot B and A prime dot B, those need to be of the same dimension. Otherwise, I can't possibly demand that they satisfy this equation. So the one systematic way of doing this is simply by saying, well, if your slices multiply together consistently to give another slice, in other words, if your dimension set has a binary operation, then you can possibly demand this. It doesn't mean it will imply it, but you can possibly demand this axiom. I guess part of what I like about this presentation is that from the moment you present dimension sets as these typed sets, you can try and perform the standard constructions of algebra and try to do ring theory, module theory, all kinds of derivations, differential operators, all that kind of business, and everything is very canonical. And so it's very nice that you can at every step interpret things physically. This is part of the power. We will see that very explicitly in a second. In fact, in the next slide. But that's exactly the intuition. So thanks Jeremy for that comment. So anyway, so we have those axioms. So it's a very natural thing to demand from this kind of object. Now, what are the main examples for this? So they are very trivial examples. Of course, any ordinary ring is a dimensioned ring with a dimension set that is just a singleton. That's trivial. And then you can also have any kind of abelian group bundle. So or a field of abelian groups, you don't need bundle structure or anything, on some set, and then that will be the zero ring on that set because you have zero multiplication. But those are very boring extreme cases. Another sort of intermediate example would be a ring times a monoid. So Cartesian product between a ring and a monoid, that will be a ring. But the most natural and the main example that I want to put forward for dimension rings, and the one that actually justifies why I'm talking about dimension algebra if I want to talk about dimensions in physics, is the one arising from the potential construction, what I call the potential construction. So the potential construction is the following. So a lot of people will be familiar with the tensor algebras of vector spaces. So here L is, I mean, this could be any vector space at this point, but these are going to be lines. So lines are one-dimensional vector spaces, and morphisms between them are invertible. So they are subcategory of vector spaces, perhaps real vector spaces for the sake of concreteness, and they form a subcategory, but they're not exactly just vector spaces because the morphisms are always invertible. So anyway, so this is not so important for this presentation, but just to remind that because it will be relevant for the Jacobi geometry part. So we build this object, just this joint union of all the tensor powers. Convention is the zeroth power is R, and the negative powers are powers of the dual. And for now, this might be a bit mysterious to you why I'm doing this, but hopefully it'll be clear in a second. Because this construction allows me to define an operation, a binary operation on the whole union of all this, so the L dot construction, that is in fact simply the tensor product, throw in the dual structure, throw in the module structure or the vector space structure. So that list basically, and then extending by linearity, defines the dot product, this circle product, which is just the tensor product in some sense. But then it mixes in so you see the few first line. The first line is for vectors, it's just tensor product. For covectors, just tensor product. For elements, scalars and vectors and covectors is the vector space structure or module structure. And then for vectors and covectors, you sort of pair with canonical pairing, right? With a dual pairing. And so this construction, which is absolutely elementary in linear algebra, turns out that if you define the obvious slice-wise operation, each of the tensor powers is a vector space, so it has an addition. I mean, it's just a vector space. So it's an abelian group in particular. So for each n, you have an abelian group, which is the tensor power. And it turns out that if you throw in this circle multiplication, which is basically an extended version of the tensor product, that you end up with a dimension ring. That's exactly the structure that you end up with when you do this construction. And so you can further show that from the category of lines, as I described, which is all the one-dimensional vector spaces with invertible morphisms, is actually functorially assigned into dimension rings under this construction. So you have a very good family of examples of dimension rings, and in fact the ones that are relevant for our discussion with physical dimension. So at this point, we already have a good mathematical model for physical quantities of k different dimensions. So basically, this potential construction you can do for a collection of lines. You just choose a canonical ordering, and then you take the tensor powers with that ordering, and you can in fact extend the circle product that I defined into this context, and this becomes a dimension ring over set n, or sorry, set k. So k copies of the integers. So this is in fact what we want if we're doing physics. I mean, I mentioned Vitolo's version of positive spaces. I recommend that if anyone is interested in seeing a mathematically modern and rigorous presentation of dimensional analysis, go read those papers, because they actually develop the entire theory of the tensor powers with rational tensor powers, and it's super nice. It's very well done. Okay, so this was the mathematical presentation. As I say, it's very minimalistic. You just begin with dimension sets and then try to reproduce what you know from the standard algebra, and you end up with these objects. It's very, very natural. I mean, if you have a look at the paper, you will see that you derive things like derivations and morphisms. Everything's super natural. But then how do we put this back into classical mechanics? So I announced that I wanted to connect to classical mechanics. So let's briefly remind ourselves what classical mechanics is in this context, geometric classical mechanics, I guess. So first of all, we have smooth manifold as our phase space. And then our observables are going to be, or typically people claim, are the real valued functions on this phase space. So this is a very common sort of simplistic approach, minimalistic approach within mathematical physics. Now, what I would like to have is I don't want to question too much the fact that we have smooth manifolds. I think they are fine as base spaces of our potential theories, but real value functions seem very limited if we want to capture what we were describing a minute ago. So I would like to have a theory that assigns observables to phase spaces as dimensioned rings. Right. This is my goal. This is what I would like to do, and so this is sort of somehow the end, the first half of my presentation. The second half and the final one, I want to present to you my idea of how you can do this very naturally by considering line bundles and doing a little detour into Jacobi geometry and contact geometry to actually end with this kind of product, right? I mean, I want a theory of mechanics that has phase spaces that are reasonably familiar in terms of what mathematical objects they are, but they naturally produce observables in the form of dimension rings. I mean, it's a very minimal requirement I am asking. So this is what I see Emily's here. So in one of our retreats with BRCP, this is where I was thinking about this for the first time, and I was doing my thesis on the other side of the story, the Jacobi geometry, and then they two sort of serendipitously got together. It was very interesting. But anyway, so let me tell you how I'm approaching this. So first, let me say what is classical mechanics, or actually I should specify what is the phase-space formulation of classical Hamiltonian kinematics. This very, very precise instead of just classical mechanics, which can have a lot of philosophical detours that we don't want to take right now. So the way I understand Hamiltonian mechanics or phase-space formulations of physics, I should say, or mechanics, is that you have three categories. You have a category of phase spaces, you have a category of observables, and you have a category of dynamics. And you have functors between them that operate in this way. So this looks very abstract, but I assure you that this will look very familiar in a second. So we call a phase-space theory Hamiltonian as long as whenever you have the observables of a fixed phase space, we have a map to the dynamics of the phase space. So if you just look at the sort of vertical functor there, we have a functor from observables to dynamics, and that's the evolution functor. EVL stands for evolution. And the Hamiltonian maps are a way of assigning dynamics to observables in a way that is dynamical. I mean, excuse the sort of redundant language. So what does this mean? This means that on the one hand, we have observables producing dynamics. This is sort of the observables generate symmetries. And on the other, we have observables generate time translations, and so they generate sort of the evolution of the system. So we have this sort of dual description, and but at this level, I just want to focus on, I will call phase theory Hamiltonian as long as I have this kind of structure and I have a Hamiltonian map which sends observables to dynamics in this traditional way. So you should already be thinking, oh yeah, this is probably the Poisson bracket and blah blah. So I'll show you in a second, because we're gonna do something a lot more specific. So don't get daunted by the big table. This is just a summary of how I understand sort of traditional configuration space mechanics, so good old Lagrangian and Hamiltonian mechanics, right? So on the left you have configuration spaces. That's the category of manifolds in the standard theory, and you have the usual constructions there. You have manifolds. You have the fact that observables on the manifold, which are just the smooth functions, and the dynamics, which are the vector fields, are naturally given once you specify a smooth manifold. Then you can take products. You can think of morphisms as smooth maps. You can take sub objects. You can take sub manifolds, and you can take forms of symmetry, reduction, etc. In this case, are just characterized as a group action. So if we are in the hunt for this kind of theory, a theory that has phase spaces, observables, dynamics, and that has this sort of Hamiltonian maps between observables and dynamics, I want to start with the most obvious choice, which is take configuration spaces, sort of where things are, right? The typical Newtonian mechanics. And then let's try and build such a Hamiltonian phase space theory. And the way we do this is we take the cotangent functor. So simple, as simple as that, right? So we take manifolds to symplectic manifolds because we take the manifold to its cotangent bundle where it has a canonical symplectic form, and so observables and dynamics of the base manifold of Q are both part of the observables as the sort of fiber-wise constant and fiber-wise linear functions in the cotangent bundle. And then you have this very nice pressure. So this is a functor. Taking the T star is a functor, but it's a functor in a very specific way because it takes all these structures into the symplectic category, right? So products of manifolds turn into symplectic products of symplectic manifolds. Morphisms turn into Lagrangian relations, which are the natural morphisms of this. By the way, when I say functor and categories in this case, it might be with an asterisk because sometimes the actual conditions might fail. But morally speaking, we're thinking of functors and categories. And so you have set manifolds that produce quasi-isotropic submanifolds, and we have reductions that produce reductions, essentially, right? So then the example is the familiar one, right? We have phase spaces as symplectic manifolds, we have observables as Poisson algebras, and we have dynamics as the vector fields over symplectic manifolds, which in this case I represent as Lie algebroids. This Lie over manifold is Lie algebroids. And you have these three functors. Again, functors maybe with caveats, but morally speaking, where we take a symplectic manifold to its Poisson algebra, we take its symplectic manifold to its tangent bundle, and then the derivations of the Poisson algebra are represented as sections of this Lie algebroid. And then, of course, the Hamiltonian map are just the usual Hamiltonian vector field assignments that we're all familiar with. You take a Hamiltonian function on the cotangent bundle, and you get the Hamiltonian vector field. So that's what the Hamiltonian map is doing. And the reason why I choose to talk about functors is because you really want to preserve the algebraic structures. You really want things to map into morphisms. You really want everything to be as compatible as possible, basically. Okay, so this is my summary of classical mechanics. This is how I think of classical mechanics. I have this broad understanding of, okay, this is my template. I want to do something new, and I want to fit it into this template and into this categorical template. And otherwise, I wouldn't be really satisfied that I have a good candidate for a theory of mechanics. Not even a useful one, but a plausible one. Okay, so what is the idea of unit-free Hamiltonian mechanics? So the idea of unit-free is that it's quite naive. In the vein of what we did in the beginning, we just say, well, let's just take a line bundle over our configuration spaces. So imagine that you just, instead of having a smooth manifold, you give a little bit extra information by saying, put a line on every point of that manifold. Intuitively, if you're thinking of real functions as being your observables, this precisely corresponds to saying, well, at each point of your manifold, you don't want to specify the one, right? You don't want to say which unit you have there. And so you just say you have a line without a preferred canonical choice of one. So you have effectively the mathematical data for a line bundle on the smooth manifold Q. And so, of course, the observables, which are the sections, we now want to think of them as unit-free functions. So observables of the sections of a line bundle have something have a property that is quite interesting for us, which is mathematically kind of trivial, but it's very important for us, which is that they don't have a constant unit on the whole space, right? And the idea is this is twofold. On the one hand, it is because bundles are not necessarily trivializable, but on the other hand, it's because they are not canonically trivializable. So whenever you give me a line bundle, I don't know what the trivialization might be. If it's trivial, you can find one, but there's no canonical choice. I mean, it's exactly the same discussion as what's the difference between R and a one-dimensional vector space. It's literally the same discussion. So that's the sort of standpoint that we're taking. We're saying we want line bundles that don't have a trivialization chosen, even if they are all trivializable. If we want to impose at some point that they are all trivializable, which we don't have to, but if we wanted to, we just say we don't choose a canonical trivialization. How do we understand the sections of a line bundle really as observables if we still want to recover something like functions and we still really want to go back to the old times of observables are real functions? The way it operates is exactly as you mentioned, by taking a local trivialization. So a local trivialization is a non-zero section, right? A local non-vanishing section for a line bundle. Yeah. And so if you take that locally, which is this community that you're speaking of, then on that local trivializations, any global or local section that is restricted to that neighborhood will be represented as a function, because by the virtue of the fact that it's a basis at every point, you would have a scalar multiple of that section at every point. So global or local sections turn into local functions whenever you introduce a trivialization, right? So that's why we are presenting observables as just sections, and we are not really specifying anything else. They are potentially local sections. I should say that they are potentially local. There's no problem in doing that. We are emphasizing here the algebraic structure and not the geometric one at this point. But that's how you go back to functions. You trivialize or choose a non-zero section, which is what we call a choice of unit, in fact. And then it's by the interplay between a choice of unit and some arbitrary section that you get sort of a real observable, right? So thanks for the question, because that's exactly the unit-free philosophy. The unit-free philosophy is we have a bundle over a manifold, and then there's no unit. That's why I call it unit-free, because there's no choice of unit. There's no preferred choice of unit. And then choosing a unit is an active it's an active choice here, right? You have to say, I choose this particular local non-vanishing section here, and if I choose that one, then all the sections have a particular representation as functions, right? So we have this theme of what in traditional classical mechanics would be just one function for the Hamiltonian. Now it's an equivalence class of infinitely many functions for the Hamiltonian, precisely given by this localization and trivialization of the line bundle, right? So, but at this point, I think that being clarified, let's just try and think that the observables are the sections, and let's see how far we can get with this, right? So this is the sort of my mathematical mindset is, let's see how much I can get for free without specifying anything else. So let's see how far I can get just by making this choice, and let's see what happens if my aim is to recover Hamiltonian phase-based theory in the sense of this triangle of functors, right? I want something like that, and I want something like the Hamiltonian functor that takes me from configuration spaces, which in this case would be line bundles, into my phase spaces, the real phase spaces where things happen. So this was my work in my thesis, which is mostly all mathematics that were very well known, but I had to flesh it out in this language to really make sure that it works as it does in the symplectic case. So basically, this table here is the analog of the same table as before, but in the contact world, right? So this is where we make contact with contact geometry, excuse for the pun, and we are taking line bundles into contact manifolds by constructing their jet bundles, right? So this is the analog of constructing the cotangent bundle in the context of line bundles. So again, you can see the constructions on the left-hand side are the typical analogs of smooth manifolds. You have line bundles, you have observables, you have dynamics, you have products, you have morphisms, you have SAP objects, and you have group actions. And then they get sent to exactly the same sort of structures within the canonical contact manifold on J1L. Right. That's. I mean, it's quite a bit of work to make sure that everything works out. To make sense of the product of line bundles is a little bit mind twisting at first, because you have to think of how this product here, L1 times L2 with a top bar on the cross, that is defined as all the pointwise invertible maps between fibers. So it's a little bit more complicated than just the Cartesian product, but it is the line version of the Cartesian product, basically. And so everything works fine at a categorical level. Everything is entirely analogous, and in fact is a strict generalization that is sort of symplectic. The symplectic case is strictly contained in this one, although that's not obvious when you first do it. And then you end up with something that looks like a phase-space triangle of functors. So you have contact manifolds, you take their sections, you get local Lie algebras, and then you take their derivations, and you end up with Jacobi algebroids, right? So this Jac over man is Jacobi algebroid, which is the line bundle analog of a Lie algebroid. Now the D is the derivation bundle, so it's the line bundle analog of the tangent bundle. Everything is entirely analogous. So we are well in business, at least kinematically, to think that unit-free Hamiltonian mechanics is looking like Hamiltonian mechanics. I mean, at this level, categorically, it really does look like Hamiltonian mechanics. And then just to top this off, we have our Poisson bracket, so to speak, which in this context we call the Jacobi bracket, in the space of sections of the jet bundle, just defined as usual, and it's, symbolically you can replace pi by, so pi, capital Pi to lowercase pi, and J1 by D, and you have literally the definition of the Poisson map. So in some sense we've succeeded. So unit 3 Hamiltonian mechanics works at a categorical level, but we're actually not quite there yet in what we wanted. Remember that we wanted something that looked like a dimension ring in the end, and that had all the basic structure of classical mechanics. So the big lacking point of observables is that they don't have any multiplicative structure. We don't know what it means to do energy times momentum, or length times velocity, or mass times density, or things like that, right? We don't know what it means to do that, because we can multiply functions, but we don't know how to multiply sections of a line bundle. And you might be thinking, oh, you can take the tensor product. Yes, we can, but then we are going outside of the original space, and so our theory is sort of breaking down in that sense. And then the other problem is that the actual object that we are identifying as our observables, which are the sections of the line bundle, doesn't resemble anything like a dimension ring. I mean, it's just a module, right? It's a C infinity module. It doesn't look like a ring. It looks like a normal module over a normal ring. It doesn't have any dimension structure to it. So this is where the potential functor comes again to the rescue. And as I said, this was the main construction that I was going to be building my discussion on. So we take the potential construction, but now for sections of the line bundle, which is this construction, this trivial, naive construction that you see there. Here, n again denotes the tensor powers, positive, negative, with the dual and all that jazz. And then you can show, with a little bit of work, that this assignment is in fact a functor from line bundles to dimension rings. So this is the exact analog of the C infinity functor that sends you from manifolds to conventional rings or commutative algebras. It's exactly that version of the functor. In fact, that functor is contained within this functor, because in the sense that smooth manifolds are a submanifold of line bundles, and you have a faithful functor in that restricts. So this functor restricts to the faithful functor C infinity, which is just looking at the dimensionless slice of your dimension rings. Because if you look at the construction at the top, you take n equals 0, what you find is sections of the trivial R bundle, which are just the smooth functions, and therefore you have all the story, the conventional smooth function story, you have it here as well. So how does the potential functor work within contact manifolds? Because we have more than just line bundles, we have contact manifolds. We've constructed this Hamiltonian functor to go from line bundles to contact manifolds, and so we have this theorem from my work. We don't have to look at the details, but basically this theorem is what it's saying is that to any Jacobi manifold there is a Poisson algebra that is associated in the dimension ring. Exactly in the same way that if you have a symplectic manifold, you naturally have a Poisson algebra on the smooth functions. Well, a Jacobi manifold has in this case, dimension Poisson algebra on the smooth functions. And so this potential construction becomes in fact a functor from Jacobi manifolds to dimension Poisson algebras. And so the moral of the story, and this is really the end of my presentation, the moral of the story is, by dropping the totality of addition, we've gained the ability to regard Jacobi manifolds as another manifestation of Poisson geometry. And this is something that, I mean, this is not related to the discussion on units and dimensions, but mathematically, this is something that it's kind of new and people didn't really understand fully. And there's a big industry of people trying to understand many different kinds of geometry as Poisson geometry. And I would say this is a very good example of that. But I think people didn't look at it because it requires, so you have to pay the price that your addition is partially defined. And so from a purely mathematical point of view, you might say, oh, that's not desirable at all, because why would you want to have such a mess of partially defined operations when you can have a nice module or a nice algebra or something like that? Well, the thing is, if you have a second motivation, which is you have another program in the back of your mind that you want to recover something like physical dimension, then this is actually good because it's going in that direction. So that's how I discovered this, because I was sort of getting influences from two directions. I thought actually these things match, and it's quite interesting. So anyway, so this is the sort of the gist of it. The reason why I introduce dimension geometry, or dimension algebra, is to be able to say, well, now I have this triangle of functors. I can go from contact manifolds into dimension Poisson algebras, and then from contact manifolds to their derivation bundles. And if you take the derivations of the dimension Poisson algebras, they always contain the derivations of the line bundle. And so, morally speaking, again, the details are kind of tricky here, because you have to make quite a few choices to make sense of these things as functors. But morally speaking, you can complete this picture, which you couldn't unless you did something like this potential functor. And then, of course, so we've answered our motivation, which was, can I have a phase-based theory in which my observables literally have the structure of a dimension ring? The answer is yes. Just play the game that I just showed. So construct the potential functor of that. So this was what I wanted to say. Now, for the mathematically inclined, I have a meme summary of what Jacobi manifolds are, and so I can tell the story in two directions. So it's a meme summary. It's literally a meme summary. So I don't want to talk any more maths. We can go into more philosophical discussion that I listed a few bullet points at the end that we can talk about. But I wanted to give a sort of a meme summary of what's happening. It's just the mathematical background to this discussion. As I said, there is this understanding that Jacobi manifolds, which by the way were first defined literally at the same time as Poisson manifolds, because it was the same author around the same time saying, look, you can have a Poisson bracket, but you can also have a Jacobi bracket, and they are both examples of the same thing. So it's kind of sad that history has made Poisson so prominent to the point that it's called Poisson geometry, and sort of the larger field is Poisson geometry or symplectic geometry, and contact and Jacobi geometry are thought of. I thought of them as separate fields almost. Some people think of there's a good way of understanding things as symplectic is the even part and contact is the odd part, and sort of symplectic happens in even dimension, or contact happens in odd dimension, this kind of thing. But actually, they seem to be part of the same story. So what happens with Jacobi? So Jacobi basically is taking a Poisson bracket that is, instead of being a derivation for functions on its entry, it's a differential operator of order 1, which is basically a derivation plus multiplication by a function. Right? So the moment you assume that you have such requirement, your Poisson bracket suddenly has two extra terms that you have to make sense of if you want to have the Jacobi identity flying around. Anyway, so the summary of what I presented in my talk today was, so Jacobi was coming to eat us, and we were prepared with our basic machinery, which were smooth manifolds. I am a geometer. Most of us studied some theoretical physics. We know smooth manifolds. So the Jacobi structures, we have smooth manifolds. Now, if you have your Jaws trivia on point, you would remember that the quote in the movie is, you're going to need a bigger boat, right? So we're going to need, in our case, a bigger category to really make sense of Jacobi. So our first attempt was to say, how about, so smooth manifold died horribly to Jacobi. They were not enough. And so we proposed unit 3 manifolds in the sense of putting line bundles on top of manifolds and thinking of the modules of sections as if they were sort of unit 3 rings of functions, right? And the problem was that we still saw that we couldn't really fully realize the theory of Jacobi manifolds because we were lacking products. For the more mathematically minded, we were lacking tensor products. There was no way to take tensor products of Jacobi algebras. If you ask a Jacobi geometer, how do you take the tensor product of your Jacobi algebras, they will tell you, well, you go to the dual, then you do the Poissonization trick, you take the tensor of the Poissons, and it's kind of a big mess. It wasn't a natural thing. You say, oh yeah, I have an algebra, I take a tensor product of an algebra, right? We didn't have that transparent of a picture. So the unit 3 manifolds still said you're gonna need a bigger category. And so finally, we presented this notion of dimension sets, this dimension rings, dimension modules, dimension algebras, blah, blah, blah. And eventually we defined the notion of dimension Poisson algebra, and that was enough. And so I prepared this little clip to illustrate how this goes about. So I'll do the play-by-play in a second. Okay, so let me do the play-by-play. So basically, we have Jacobi is coming to eat us, and then we have dimension categories. We have the dimension machinery that I presented. This idea of taking type things and sort of paying the price of partial addition, and then we aim directly at something that is really within Jacobi is the potential functor. Jacobi carries the potential functor inside it. I mean, it's just looking at the tensor powers and constructing. So many mathematicians have told me, why do you take the disjoint union and not the direct sum? Right? I mean, we all do the tensor algebra of a vector space. Why don't you just take the direct sum? And I said, well, because categorically I want to have these kind of structures, and they only happen when I take the disjoint sum, the disjoint union, and then I recover this dimension structure. So the potential functor was there, and so we literally exploit, in this case, the potential functor, and then dimension categories win, and Jacobi is done. So dimension categories win over Jacobi, right? So that's the picture. Anyway, so that's the end of it. Thanks.